So this is the last section, and today we'll be covering 3 major topics: graphs, hashing, and sorting. All right. So yeah, these 3 major topics, they are on the exam, so make sure you study them. You won't get coding questions. It's mostly just conceptual questions. So today we'll be doing mostly just conceptual questions, which is why the board's not there. Are there any other topics you want me to particularly review? Because I can do that instead. If like you've already studied hashing and graphs and something else, I can review something else. Okay, and as a reminder, I have a review session at 3:30 in Gates 200, so upstairs. If you want to go there, feel free to go. Okay.
Please turn your mic on.
Oh, not on. There we go. Test. Okay. All right. So yeah. So review session. Make sure you go to 3:30. Yes.
Covered on the test tube, but conceptually.
Conceptually, yes.
Okay.
Mm-hmm. Should I go over tries?
Yeah.
Yes? Okay, everyone agree? Go over tries? Okay, awesome. So I'll start by going over tries then. Okay? So general idea of tries is that to store a word, to store like a string, for example, okay? Tries are how lexicons are backed. Lexicons have 3 major operations. Lexicons, they have add, so you add a word. They have something called contains, and then they have a third major operation called contains prefix. Okay, so add and contains, they work just like sets, but for contains prefix, this one you've used in, I think you probably used this in Boggle, where you wanted to check if the string you built up so far is in your lexicon. Now, regular sets, if you implemented this as a regular set, so a binary search tree, you could implement these 2 in O of log n time really fast, but this one is a little harder to implement. Okay, so the key idea we're going to do here is we're going to implement it in a way that makes contains prefix really fast. Okay, and the core idea is this. Suppose you had like a couple words, cat, cad, car, core. Right, they all share some sort of prefix, right? Like these share a prefix CA. So the way we represent it is we draw the nodes like this. Okay, each node represents like a collection of letters so far, and then each edge represents a new letter you add. So initially, our word is just the empty string, and then each edge or each pointer represents a new character to add. So for example, here, the next letter is going to be C, so we're going to have one pointer C over here. Okay, does that make sense? Let's see, we don't have any other letters, so for the first letter, we don't have any other nodes. Now, in here, so this string represents C. What will its children be if we added these words? A and O, right? Yeah, so because we want to build up the words CA and CO, so we have an A over here, and then we have an O. So this is CA, this is CO. And in the same way, you can just keep building this tree. So for example, here you would have COR, CORE, okay? And then here you would have this would be T, R. You probably want to do them in order. So D, R, S, T, R, S. So R goes first, then T. Cad, car, cat. Okay, does that make sense? So this would be what a try would look like if you build like that. Now, sometimes when you're looking at this, you're like, okay, so which ones of these are words? Which one of these aren't words? Right? So then one thing you have to do here is inside this try, in each node, you would store a single Boolean, which signifies whether or not this is a word. So for example, here we would have true, 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 because these are all words, and then these would be false. Okay. Now, a natural question you have for this is, okay, how do I, is it possible that all the words are just, all the leaves are the words? Is that true? Are all the leaves going to be words? So that depends on if you have to remove words. If you remove words, then possibly some of the leaves aren't words. But in general, here all the leaves are words. But is it possible to have words, but the node themselves are not leaves? Is that possible? Yeah, that is possible, right? It depends on what you add to your lexicon. For example, I could add, let's just add cars, right? If we add cars, that would make a new one over here, S, cars. This would be true. But notice that car itself is now not a leaf. All right, so the reason why we have to store all these booleans is we have to signify which pointers are words, which ones are not, which nodes. Okay? Okay, so how would you implement contains prefix? So if I asked you, is CA a prefix? The answer is yes, but how do you know that? By looking at the tree. Yes? Yeah.
There's a path to trace from C to A.
Yes. So you know that CA is a word because there is a node here that is CA. If there's a node here, then that means they must have children, which some sort of children down here that have words, that are words. Okay. If I asked you instead, is CU a prefix? Well, here no, because you can go to C, but then you can't get to U. The U node doesn't exist, which means it's not it's not a prefix. Does that make sense? This is the general idea of how to implement a trie. Now, okay, other questions. How would you print out all the words in alphabetical order? In a normal BST, how would you print out all the words in alphabetical order? Yeah, a traversal, right? Specifically, you would do, if you want alphabetical order, it would be an in-order traversal. Okay, yeah. You can do the same thing over here, where essentially you would trace the tree like this, and you can hit, okay, CAD, then you hit this one, CARS, CAR, CA, and so on, okay? This kind of traversal will go through you will go through all the nodes, and then you can try to figure out which ones are words, which ones aren't words. Okay, does that make sense? Okay, last question. How would you implement these? So as you can see, these aren't binary trees because you could have multiple children. So do you remember how Tyler implemented it? Call this a trinode. What do you store in each trinode? Yes?
The letter, or like I guess the string that it holds.
Okay, so string, let's call it like the word or letters.
True or false, whether it's in it.
Okay, Boolean is word.
And then you have a lot of pointers for each of the different letters that could be added.
Yeah, exactly. There are a couple ways you can store that. Like an easy way would be you can do a vector of characters, a vector of pointers. So that would be you would do a vector of trinode pointers. I guess children. Okay, so that would represent like all of these. Another way you could do it, this is one way you could do it. Another way you could do it, I think a better way is to use a map. So you would map each character to a trinode. Okay. There's also a third way I've seen it, and I think that's how Tyler did it in class, which is he used a trinode pointer array, something like this. Right? He had an array of trinode pointers, and specifically he had 26 of them. Right? So he had 26 possible children, and then you would put the pointer to the child in the right place. Okay. Do you have any questions about this? Yeah. Okay. You don't have to code it up, but you just have to know conceptually how they work. All right. If you don't have any other questions, do you want to try? Let's try doing a graph searches. All right. So what were the 3 kinds of graph searches you learned? Yes. Mm-hmm. Okay, DFS. So let's do DFS first, okay? The key idea of DFS is you commit to choices, and then you just keep exploring it until you reach a dead end, then you backtrack. It's kind of like how we did recursive backtracking, right? You commit to a choice. You ignore all the other choices. You commit to that choice, explore as deep as you can until you either find an answer or you failed. Then you go back to that decision point and you make another choice. Okay. For that reason, DFS is often implemented recursively. It looks almost the same as recursive backtracking code. Okay. All right. On the exam, you'll also see something like this, which is like if you're running a search, you would go through them in alphabetical order. Okay. So for example, if we started at A, let's say we were searching for a path to go to I. Right? So we start at A, and then we're going to explore all of its neighbors in alphabetical order. So if we were going through this alphabetically, what would the first neighbor you explore be? B, right? Yeah. So here we say, okay, we visited A. We're going to go to B. Okay, and then we're going to go as deep as possible, right? We're now at B. We want to keep going downwards. So from B, where can we go? F, okay. From F, where can we go? H, right? Okay. After H. Yes, you can go to I, but remember, because we're going through the neighbors alphabetically, there's another neighbor we have to go to first. G, right? Yeah, let's go to G first. Okay, from G. D, right? Okay. Okay. What's next? Yeah, so yeah, we can't go to E because these are single directional arrows, so we would have to backtrack in this case, right? Yeah, so we would say, okay, we give up, we go back one, so we go to G. Okay. Okay, and then from E. So yeah, we won't go to D because we've been there already. Where else can we go? Yeah, so when we unchose, we only unchose one step. We went from D back to G, but we haven't unchosen any of these steps. You only unchoose after you've explored the entire tree, and then you go back upwards, right? So we were at G, right? So we went to D, that failed, so we unchose that one, and then we're going to go back to E. Oh yeah, I see what you mean. You don't have to go back to D because you only have to explore each node once, right? Once you've been to that node and you know that node doesn't work, then you know that your path is not going to go through that node. Yeah, okay, good question. So we're at E. Where else can we go? C. Right, we can go to C. What happens at C? What happens at C? Backtrack, right? Because we can't go anywhere. Go back to E and then to I think. Yeah, we've been to G. We've been to H. Yeah, we go to I. So that would be here. And we're done. Okay, so this, Tyler doesn't explain it this way, but what I like to do is I like to draw the tree in which you explored. So we went from A to B to F to H to G to D. We failed, we backtracked. And we went to E to C, backtracked, we went to I. Okay, questions are usually going to be of the sort, okay, in what order did you explore the nodes? In what order did we explore the nodes? Mm-hmm. Yeah, exactly. That would be just a traversal of this, right? So we can just write it as a traversal, B, F, pre-order traversal, I guess. E, C, I. Okay? All right, what is the path? So DFS is going to return a path. What path will it return? It should be clear what the path is looking at this diagram, right? So what is that path? Yep, exactly. Okay? Yeah, so yeah, Tyler doesn't explain it this way, but I like to draw the tree out so you can visually see what the backtracking is. And then you can also easily find what the order is, just to a pre-order traversal. A path is also easy to find, just see how do you go from A to I. What I really like about this is also, if I asked you, suppose I wanted to go from A to D, well, what would the path be? Well, that's clear, right? Just go A, go down to D. All right, all the DFS, no matter if you start at A, no matter where you want to go, you can go to any point just by looking at this tree. Okay, does that make sense? Yes.
Which one you're gonna go to though? Like, if you're A, how do you choose like B as opposed to E or D?
Good question. So on the exam, I think they'll mention that because these like if you implemented this would be like a for each loop. You would loop over all the neighbors, and then the order in which you loop over the neighbors would be alphabetical. So if you have like a lot of neighbors, then you prioritize the one that is like A or like B. B is ahead of D. Okay. Question? Yes.
DFS takes care of the cost.
DFS does not take care of costs.
Okay.
Yeah, so when you're asked to do a DFS, you'll probably be given a graph. They might tell you, okay, just ignore the edges. Yeah, exactly. And notice, is this the shortest path? Like, even if you just ignore the weights. Right? The shortest path is, if you ignore the weights, is just A, E, I. And we'll see that when we do BFS. But for DFS, that doesn't take care of the heights. Okay, does that make sense? Okay, let's see. Let's do BFS. Okay. So BFS is similar, but the idea is that instead of going as deep as possible, you're going to branch out on all your neighbors immediately. And then in each iteration, you'll branch out more through your neighbors. So for example, for BFS, we start at A. What are the neighbors we have to branch out to? B, D, and E, right? These are the neighbors we can branch out to. So B, D, E. All right, starting at B, where can we branch out next? F, right? F. Okay, starting from D, where can we branch out to? H, okay. Okay, starting from E, where can we branch out to? Go to, so let's see, we can go to F. Yeah, we start with C first. C, F. We don't need to go to H because we've been there. Let's see, F. Yes, we've been to F also, so we don't need this one as well. Let me just double check I'm doing this right. Yeah. A, B, D. Am I doing this wrong? Let's see, B should be able to go to. Yep, okay, that looks right. And then C can also, E can also go to I, right? Okay. All right, so let's see. And then once you find that one, you know that you're done because you've because we're now at I. Okay. In what order did we visit the nodes? We haven't gone through G. That's a good point. Okay. I think on the exam, what you can do is once you reach I, you can stop. Yeah, but if you wanted to go through all the nodes, then you would go F. F doesn't go anywhere. H can go to G. Yeah. Yeah, we're gonna say the question will say something like, okay, run a DFS to find a path between A and I. In which case you would just go to up I and then you can stop. In what order did we visit the nodes? Start with A. B. Exactly. Okay. We don't need the G because when we reach I, you can stop. Notice what kind of pattern do you see? Yeah, top to bottom, left to right. Okay, and that's because the order I'm drawing these in, I'm going to go through like the for each loop goes through them in alphabetical order. Okay, what do you notice about these levels? So this level, and this level. Like what's true about F, H, C, and I? They're all on the same level.
They have the same length from A.
Yeah, exactly. The path length from A to any of these is going to be 2. Okay, and you can actually see what the path is. Let's just write the path down. What's the path from A to I? Okay, does that make sense? So to any node here, it takes a path length of 2 to get to. BFS on an unweighted graph, so if you just remove all the weights, BFS will give you the shortest path. Are there any questions at this point? Okay, let's do Dijkstra's. So do you remember what Dijkstra's finds? Yeah, Dijkstra's. Okay, Dijkstra's finds the shortest path, the shortest weighted path. Okay, so this might be the shortest path in terms of number of edges, but the shortest path is the path which has the lowest sum. That's how Google Maps works. Okay. All right. So Dijkstra's, the key difference is that instead of adding like going through the neighbors like this, what you should be doing is you should be keeping a list of potential candidates to extend. You always want to be extending the shortest candidate we have so far. Okay. So that's a little hard to explain, but let me just go through this one more time. So starting from A, what are some candidates we have to go next? B, D, and E, right? Okay, so I'm going to draw them in dotted lines because we're not actually committing to them yet, but we're just, these are just potential candidates. Oops, let's do B, D, and E. Okay, and their lengths are 43, 6, and 12. Okay, and the key thing at each point is, okay, look at all the candidates you have. Which one is the shortest one? D, right? Okay, so when you know that, then you commit to it. I'm going to use a different color. I'm going to commit to this one. And when that happens, then you check it off. D. Once you commit to one, then you add all of the neighbors starting from D. So what would the neighbors would you add? Just H, right? So H is now a candidate that we can move forward. 84. Okay. All right. At each point, now you look at all the candidates again. Which one's the best one? The shortest one.
So we do E.
E, yes, that would be E. So we would commit to E, and then we'd mark E off as visited. Since we just added E, now we're going to add all of its neighbors. So what are the neighbors of E?
C.
Okay, we can add C.
I.
So C has weight 15.
Should it be in there? D.
Good question. Let's see. Let's put D and let's put B. So you don't have to put D because D we explicitly said, okay, we already committed to that. So you don't have to add D. B, on the other hand, we never committed to B, right? We added it as a candidate, but we never committed to it. So let's write B down, and B has weight 2. What other ones are there? H and I. H has weight 51, and I has weight 77. And F, yes, F, which is to there, 39, okay. Okay. The thing to know is we've already added B. So what you should do is you should look at B and think, okay, is this one better than that one? Is this B better than that B? Yeah, by a lot, right? So when that happens, you remove the worst one. Okay? Does that make sense? Okay. Someone walk me through the next step. What would you do next? First step is always figure out the smallest candidate, the best candidate. Which is the best candidate?
B.
B, yeah. So let's just commit to B. So we're going to check B off. Okay, second step. Sorry?
The neighbors.
Neighbors of B? Yeah, exactly. So which one are the neighbors of B? F, okay. It has weight 48. Okay. So notice we have two Fs. So what do you do in the case you have two Fs? We have an F. Yeah. Uh-huh.
Sorry. Eliminate the larger one.
Yeah, so which one's larger?
This-
This one's larger because 12 plus 2 plus 48, that one is worse than 12 plus 39. So we remove that one.
H's also.
Yes, we should have. So which one is worse? Yeah, 6 plus 84 is worse, right? So we remove this one, okay? All right, anything else for B that we have to add? I think that's it, right? Okay, next candidate. C, yeah. Okay, so let's do C. C, check C off. All right, now that we add the neighbors of C, what are the neighbors of C? B and F, right? So B we have not visited, so let's, well, B we already committed to, so we're not going to do B, but we haven't added, well, we haven't committed to F, so we do want to add F. 7. Okay, which one's better? This one or that one? The new one is better, right? Because 12 plus 15 plus 7, that's less than 12 plus 39. So in that case, we want to keep this one, and you want to delete this one. Okay, make sense so far? All right, what's our next candidate? Which dotted line remaining is the shortest one? So we have 12 plus 15 plus 7, or 12 plus 51, or 12 plus 77. Which one's better? This one, right? Okay, so let's commit to that one. So F went to F. Okay, and then what do you do with F? Okay, we're going to add an H. Okay, let me move this up a little so I don't have space. So F. And our candidate is H. What is the 19? Okay, we have two H's. Which one's better? The new one, right? Because 19 plus 7 plus 15 plus 12, that's less than 12 plus 77. No, not 77, 51. So this one's not the one we want. We delete this one. All right, what's next? Next candidate. There are only two more candidates to think about. So this is tricky. Let's see. 12 plus 15, that's 27, 34, 54, 53 versus something 77. So this one's better. I commit to this one. H. Okay, and then what do we add at H? We add the neighbors, right? What are the neighbors? I and G, right? Okay. Do we add G? Yes, we have to add G because G's not on here yet. Okay, I is 64 and G is 5. Okay, last. Which one's better? The best candidate is G, right? Out of the candidates, G, I, and... Oh, wait. Before we go on, which I is better? The old one. The old one is shorter than the new one. So we're going to delete the new one. All right, best better candidate. Which candidate is better? The G is better, so we're going to commit to G. G is... Okay. And then what do we add? We add I, right? We add E, but we already committed to E, so we're good. We add D, but D is already committed, so we add I. Oops, should be blue. I. And I is 30. All right. One more step. Which one is better? The I here or the I all the way down there? The old one's better? Let's check. 12 plus, okay, well, these are both 12, so let's ignore that. 15 plus 7, that's 22. Plus 19, that's 22 plus 19, 22, 42, 41, 46, 76. So that one is one shorter than this one. So you commit to that one. And check it out, we're at I, so we're done. Okay, that was really long. So what was the, when you do this question, I suggest you write down the order in which you you check off the nodes as you're doing this, because it's hard to figure out what the order exactly we did. Okay, but if you just quickly think about what order we did, what was the order? We started at A. We went to D first, right? Then we went to E. And then from E, we were like, okay, let's go to B. But B didn't work, so we go to C. And then all the way down, H, G, I. Let me just double check, just make sure that's right. A, B, wrong one. This one is the one. A, D, E, B, C, F, H, G, I. Yeah, okay? And then what's the path we found? Okay, that's just the screen path you saw over here. Okay, so yeah, so on the exam, you'll get a question like this. It's not going to be as complicated as this. You'll have like half as many nodes probably. Half as many nodes, half as many edges. But it's the same process, and even though this does look complicated, but there's like that systematic way of doing this. All right. Compare this to the algorithm you did in class. What similarities do you see? These are the exact same algorithms, but I'm just drawing it graphically like this. So first we pick the best candidate, right? What is that the same in Dijkstra's algorithm? That's like dequeuing from a priority queue, right? The priority queue, the priorities are like the distances. So by dequeuing from a priority queue, you're dequeuing what the shortest candidate is. Given that candidate, you add all of its neighbors into the priority queue. That's like adding a bunch of candidates over here. Specifically, the priority you add was the original priority of the thing plus the distance to that neighbor. So for example, when we added like all these neighbors, that's the same as enqueuing C with priority 12 plus 15, B with priority plus 12 plus 2, and H with priority 12 plus 51. So that's the enqueue step. Then you just repeat that process, right? Then you dequeue the best candidate, whichever one that was. You go through its neighbors, and you enqueue all of its neighbors with the priorities, that entire sum. Does that make sense? See how this algorithm is just this like the graphical version of Dijkstra's. Okay. All right. Any questions so far? So this is definitely going to be on the exam, the graphs. So make sure you study it. No questions? Okay. So we're going to cover, we can either do graphs or, not graphs, hashing or sorting. Which one do you feel less comfortable with? Preference? Sorting? Hashing? Don't care? Whichever one's more important on the final? They're both important, so, okay. Fine. Okay, any of you remember what sorting is? Yes, no, maybe, a little. Okay, how about hashing? I just wanted to think which one's less familiar. Okay, everyone's non-responsive. Let's quickly talk about hashing then. So hashing, first, why do we need hashing? What's the purpose of hashing?
Faster search.
Faster search, right? Specifically how fast? That would be sorting, right? And login is in the sorting. Yeah. O of 1, exactly. Okay, it's really fast. And how is it so fast? Why is it O of 1? Yeah, exactly. So it's because you're storing the elements based on like indices, and it's really fast to look up something at an index. So that's why hashing is O of 1. The idea is you're going to have this thing called a hash code. This is very important, hash code, which converts your elements into indices. Okay, a very common one used if these are ints you often see the hash function elem mod 10. Okay, this is like on the exams, you'll often see this hash function, which is just you have 10 buckets, and then you just want to take the elem, mod it by 10, and put it in whatever its remainder is. Okay. Now, hash codes have to satisfy two important properties. All right, do you remember what the properties are? Deterministic, okay. Did you have the other one? No? Okay. Deterministic. Do you want to explain what deterministic means? Okay.
Sure.
That's fine. Any?
One output.
Yeah, exactly. So for example, if I input 7 as my as into my hash code, then if I get the index 7, then next time when I come here and put 7 in, I should also get 7 back. 7's not a good number. Like 55. If I put 55 in here, I get 5 out, right? If I put 55 in here again, like a second time when I want to retrieve my item, I should still get 5. Okay, that's deterministic. Do you remember what the other one was? Well distributed, exactly. Well distributed. And what does well distributed mean? Exactly. So out of all the elements you could possibly have, you're going to distribute them relatively equally across all the buckets. Okay? So let's look at some examples. And later I'm going to try to go through why that's important. So first, examples of hash codes. Let's do int hash code. This is a little small. Int hash code. We're going to be hashing strings. Word. Okay, the first hash code I give you is return 0. Is it deterministic? Yes, it always returns 0. Well distributed? Because it always returns 0. So everything's going to be hashed to one bucket, which is not what you want. Okay, other one. How about return random integer between 0 and 10? Deterministic? Yeah, this is not deterministic because it's random. Okay, it is well distributed because it distributes everything equally across 10, but that's not good. And then the last one I give you, this one's a little trickier. Recall that characters inside strings, these characters are also like ASCII values, they're ints. So suppose I'd said, okay, int sum equals 0. If, let's see, for each character, ch in the word, I want you to add sum plus equals ch. Okay, just so as an example, if I gave you ABC, then this is like 97, 98, 99. So what you would do is you would just add these ASCII values. Okay, and then at the end, you can just return some mod 10 or something. So for example, this one, if you sum, it's like 1 something that ends with a 8 times 3 is 4. So if you modify 10, it would give you 4. So you would put it in index 4. Okay, deterministic, right? If you give ABC, you're going to calculate it the same way every time. So it's deterministic. Is it well distributed? It's a really tough question. Yes. Who thinks yes? Who thinks no? All right, everyone's like kind of. Okay, yeah. The answer is, so this is much better than the original one. And this is actually an okay hash function. It's not super well distributed because, can anyone see what cases would you get where the hash code is not super well distributed? Yeah.
We've got same characters with different permutations.
Yeah. So for example, if I just if I take ABC and I do CBA, that gives you the exact same hash code, right? Which means like all the anagrams of a certain word are going to be hashed to the same bucket. Yeah, and that's like not well distributed, so we don't. So this is like a little hard because it's not like if you permute the letters, you'll still get the same hash code. Okay, does that make sense? The key idea here is don't write your own hash codes. Okay, any hash code you come up with is probably not going to be good and well distributed enough. Yeah.
But this hash code, this function, I think is a complexity of log n. So.
Yeah, I see what you mean. Yeah. So this is also slow. Okay. All right, any questions? Okay. All right. Let's think about why is it important for it to be well distributed. So, for example, if I give you a hash 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. That's perfect. Okay. So suppose we were hashing integers and we did the elums mod 10, right? Suppose like if you got a number of numbers, so like 50. Okay. Then we add like 60. What would change with this bucket? Yeah, you would move this down, but the thing is, you want to change it so that you add it to the front. So 60, then 50. Okay? Remember for linked list, adding to the front is much faster than adding to the back because you can just change the front pointers. Okay? Now, think about hash tables. What would the worst case be? So if I just kept adding elements, on average, if your hash function is good, you should get like O of 1 time because they're equally well distributed across all of them. But what is the worst case? What is the worst case that could happen when you're hashing these numbers? For example, yeah. It goes into one bucket. So the first example we did, return 0. What that does is it hashes everything to 0. And what happens there? Yeah, you basically have a linked list, right? And what's the runtime of that? How do you find an element in a linked list? O of n, yeah, because you have to go through all the elements. Faster is if you distribute everything approximately equally. If you're looking for like something that ends with a 6, you can just go to the 6th one and look through all of them. There should be relatively few of them. Okay? Does that make sense? Okay, let's see. So we have like 6 minutes. Are there any other questions I can answer? Any questions about the exam? About the, yeah, any questions about the exam? Yeah.
What sort of questions are we going to have on graphs? Like,
Graphs?
is it only definitions or something else?
Yeah, so you're only going to get like read questions, which essentially you'll probably be given some sort of, it might be short answer. It might be, here's a graph. Now figure out what we did, right? Figure out a breadth first search from here to here. Figure out a depth first search from here to here. Dijkstra's. Tyler also briefly covered like some definitions. So you might be asked, what's a connected graph? What's a disconnected graph? What's a weighted versus unweighted graph? What's the term? Directional? Is it called directional? Yeah, directed and undirected graph. For example, the graph that we drew, is that a directed or undirected graph? Directed, because the arrows point in one direction. Okay, yeah, question?
All the arrows are kind of both ways, but there's just one that's one way. It's still directed, right? There's like one arrow that has like one side.
Yes, although, so, yes. So if one of the arrows has only one side, then that is a directed graph, yeah. Undirected graphs must satisfy the property that, think about a friend list, right? If I'm a friend with you, you must be a friend with me. If you violate that in any way, then it's a directed graph. I don't think they'll be tricky enough to give you like arrows with both sides, but it's still like undirected. Yeah, if you don't see arrows, then it's probably going to be undirected. Okay. Yes, question? Question? Yes.
What's the read-write breakdown for the final?
I'd say similar to the midterm. Yeah, so approximately half and half. Yeah. Yeah, you'll definitely get a major question on all the topics. So if we go through like linked lists, you'll definitely get questions on that. You'll definitely get questions on trees. You might get a backtracking question. You might get an ADT question, and then you won't get graphs questions. Yeah, you might get a class design questions. So for example, you had to implement tiles. Yeah, I strongly suggest the assignments, assignment 5 and 6, and 7 kind of. They're all super important. So you probably want to review some of those assignments. Okay, review what you did, review what mistakes you did, because very possibly you'll see something really similar. Like implement a similar class, slightly different but similar. Okay. Any other questions? Yeah. This is a little bit different from the midterm in that the midterm is kind of short, it's like 6 questions. Right? The final is going to be much longer. So what I recommend is even if you're stuck on a question, like if you just completely forget how to do Dijkstra's, don't worry. That's like a very small part of a really long exam. So just go through the exam, grab all the points you have, then you can start agonizing about the ones you don't remember, like Dijkstra's. Okay? Question, yeah?
If we're going to implement heap, will it just tell you about some like how to add things or how to do some sort of operations on it, like assignment?
Let's see. So if they wanted you to do something with a binary heap, you're expected to know how like add, remove, like how the bubble up, bubble down works. Yeah. Like some of the practice questions was here's a heap. Draw what happens when I add this thing to it. Then you have to know like, oh, that's bubbling down this way, and so on. Yeah. Question. Yeah. Yes, I will. Mm-hmm. Yeah. If they want you to implement some other kind of heap, which probably won't happen, but if they tell you, okay, implement a left binomial heap or something, then they'll tell you exactly what to do then. Yeah. Probably not because that's as tough as A5, so I don't think they'll give you the entire A5. They give you like a small part maybe. Okay. What other questions do you have? You all seem kind of tired. Almost there. One more day. Less than 1 day. Okay. All right. Let's see. No more questions? Any random questions? How's the class? Okay. Are you all taking any other finals? No? Yes. Are the finals tomorrow or Saturday? Okay. So you have some breathing room between the finals. Okay. All right. Okay. Cool. Can we all take a photo? So I take a photo with all my sectionies. So I was wondering if you could all do that. For SCPD students, thanks for watching, and I won't see you next week. So good luck on the final.